All right, so we're going to do implicit differentiation here. And you use implicit differentiation when there's a y that's hard to isolate, or a y in multiple places. It's just hard to isolate y. So I have a situation such as this. So I'm going to go ahead and do some derivatives through here. There's going to be one part that's going to be a little weird about implicit differentiation. I'm going to come back and explain that. Let's just take the derivative with respect to x here. So the derivative of 2x cubed, of course, is 6x squared. That's just the power rule. Here we do need the product rule. The derivative of 2 of x squared is 2x, okay, times the y unchanged. And we want to add to that the first one unchanged times the derivative of y. Now, the derivative of y, we want to take the derivative with respect to x, but we have a y here. So what I'm going to do is not worry about that for now. We're just going to take the derivative of y as if it were an x. The derivative of y is just 1. So I'm going to put times 1 to illustrate that. But what I'm going to have to do is put a dy dx on here. And that's the part that we're going to explain in more detail in just a moment. Where does this weird dy dx come from? Okay, plus y cubed. So this is the completion of this little product rule. Derivative of the first times the second unchanged plus the derivative of the second times the first unchanged. Now the derivative of y cubed, again, if we just pretend like y is an x, and just so the derivative of x cubed would be 3x squared. So the derivative of y cubed, we're going to say, is 3y squared. But again, we have this little weird dy dx. And don't forget to take the derivative of 1. The derivative with respect to a variable of a number, it's got to be 0, right? The number never changes. Okay. So what's going on with these little weird dy dx's? To explain that, I'm going to look at the y cubed part because I don't want to get I don't want the product rule to muddle this part up too much. So let me illustrate why the derivative of y cubed is 3y squared dy dx. What's up with that dy dx? Okay, let's go to a different board to show that. All right. So what I'm doing here actually is taking the derivative with respect to x of something. Okay, that's the notation for it. But our problem is we have a y, not an x. Okay, so what we do instead then, and I like to write it this way because of the concept of fractions, it's easy to follow. It would be like taking the derivative with respect to y, but from a fractional standpoint, if I were to multiply this by dy dx, okay, and think about fractions here. If I thought of this solely as fractions, the dy's would cancel, which in a sense they do if you think about little incrementals. But the dy's would cancel, leaving behind d over dx. And that's actually what I did here. When I take the derivative with respect to x, I'm going to first take the derivative with respect to y. So that means I just take the derivative like I normally do, 3y squared. This is dy, or the derivative with respect to y. But to compensate that, because I'm taking for the entire problem, I'm taking d dx, which is really what I want to do. Since I instead did d dy, I've got to put this part with it. Okay, so what I actually did was I took this of the problem, and that, as illustrated here, is the derivative with respect to x. But again, since I did it with y, I have to compensate by putting that part beside it. Okay, I know that can be a bit mind-numbing there a little bit, but that's why we stick a dy dx on it. A lot of people are very successful at implicit differentiation, and they never really understand that. They just use a simple but highly effective rule. They just say, I'm just going to take the derivative like I always do. If I see a y, I'm just going to stick a dy dx on it. But the other board, I try to explain why that is. Now, some teachers do like to say y prime instead of dy dx. For me, y and y prime always looked too much alike, and I made mistakes when I did that. So what I'm going to do here is just some algebra, which can get a little muddled because there's a lot of stuff here. But basically, we keep dy dx, that stuff together, and the other stuff on the other side. So I'm going to go ahead and move the 6x squared and the 2xy over here. Okay, so that's going to leave behind x squared dy dx and 3y squared dy dx. And all right, negative 6x squared minus 2xy. And what I did was, I just subtracted it from 0. I just don't quite have the room here to show you. Right, but that's the other side now. Okay. And I'll push it over a little bit. But we can just factor out a dy dx, leaving behind this. And you'll develop a sense. Once you've done some of these, you can sort of bypass some of the algebra work. It's not necessary to show, okay, I've got to divide, so let me divide both sides. When you get to calculus, a lot of times you can bypass some of that work, which I'll do here a little bit. Dy dx, which is what the question wanted. I never did write the instructions, but we're looking for the derivative of y with respect to x. It's going to be this divided by this. So negative 6x squared minus 2xy divided by this, which is one big factor. And some instructors will require you to simplify this a bit more, which is one of the big issues in calculus. When are you done? When is the simplification sufficient? But here, as you can see, we can factor out a negative 2x out of there. All right, we'd have 3, that's an x. You have 3x, what would that be, plus y? And then just keep the denominator. So I'm not saying that you absolutely have to go to this very last step. You may have some instructors which say that this is sufficient, but others may insist on you simplifying to a certain point. So just be aware of that. But our final answer is usually a combination of x's and y's. But if you have a y that's hard to isolate, then implicit differentiation is the technique that's widely used.